Hello and welcome to Chapter 11.1 from Stevens' Introduction to Statistics, the Think and Do book. In this chapter we're going to do a chi-squared test for goodness of fit. And what that means is we're going to test whether or not the frequency of observed events fits what we expect. So we'll start with a preliminary example. Suppose you roll a single six-sided die 60 times, right? The outcomes on a six-sided die are 1 through 6, right? You roll it 60 times and you get the frequency of outcomes given in the first two columns. So if you look at this, so when you roll it 60 times, you got 7 ones, 6 twos, 11 threes, 15 fours, 13 fives, and 8 sixes, right? And so what we're going to test is whether those observed outcomes match or fit what we would expect. Now, if this is a fair die, you would expect the probability of each one of these outcomes to be 1/6. And so, if we roll a fair die 60 times, we would expect 1/6 of them, or 10 ones, 10 twos, 10 threes, 10 fours, 10 fives, 10 sixes. Right, so these are the expected outcomes, and of course that's not going to happen, because there's random variation. But what we want to do is say, is this far enough away from what we expect to say that there's something wrong here? Does it not fit the expected frequencies? Right, so it's a test for a goodness of fit. Right, that's why this is called a goodness of fit test. Okay. So, notation and formula. So the test statistic is called chi-squared. All right, it's the Greek letter chi squared. And I'll go over this formula. There's a lot going on in the formula. So let's look at some of the variables. N, which is actually not in the formula, is the number of trials. And in my example, my preliminary example, it's the total number of times I rolled this die. It's the total number of trials. K, on the other hand, and there's a K in here because you're adding up these things K times. That is the number of different outcomes, right? So there are actually 6 different outcomes here, and I will represent the individual outcomes. So I, and I. So the first outcomes, second outcomes, I will increment all the way from 1 to, in this case, 6. All right. O sub I is the observed frequency of outcome I. For example, 7 is the observed frequency of outcome 1. Right. Fortunately, in this case, the outcome is the number on the die, which also happens to correspond to the letter I. That obviously won't always be the case. And 11 is the observed frequency for outcome 3. P sub I is the assumed probability of outcome I. So in this case, all of our P sub i's are the same. They're 1/6. Right? E sub I is the expected frequency of each outcome. And we got all of these by taking 1/6 times n, which is 60, and we got the expected frequencies 10. And again, since all of the probabilities were equal, all of our expected frequencies were the same as well. All right? Do we have any others? Yes, the degree of freedom. We're going to be using another table that requires the degrees of freedom. And in this case, it's not n minus 1, it's k minus 1. It's the number of different outcomes minus 1, not the number of trials. Alpha is the significance level of the test, and chi-squared sub alpha is the critical value of alpha for a given significance level, alpha, and it will determine the rejection region. Just like critical values in chapters 8 and 9 determine rejection regions, the critical value of chi-squared will determine the rejection region. Right? So we'll take our test statistic, chi-squared, compare it to the critical value, and if our test statistic is in the rejection region, we will end up rejecting the null hypothesis, which we will get to in a moment. Okay, so the chi-squared distribution, this is table 5 and it's on page 293. Right? And so let's just take a look at that table. And what that table gives us is a chi-squared distribution. It looks like that. It's not symmetric. All the values are positive. And these values in here, say that 9.48, that's a critical value. That is a chi-squared sub alpha. And what you do is you take your test statistic chi-squared. If it happens to be over here, it's in the rejection region. And if it's over here, it's not in the rejection region. Right? So all of the hypothesis tests going on are right-tailed, and the rejection region is to the right of the critical value. Right? So unlike our other hypothesis test, it's not, we don't have to worry about left tail, right tail, or two-tailed. It's always a right-tail test. Okay. So that covers a lot of the stuff that was right here. The shape depends on the degrees of freedom. Oh, by the way, and the degrees of freedom determines what row. Right? And the degrees of freedom, depending on what chapter in, will be calculated differently. So you find your degrees of freedom, your significance level, 0.1, 0.05, or 0.01, and then whichever one, this row and that column will determine the critical value. So the degrees of freedom are important. The distribution is not symmetric. All of these values are positive, greater than 0. All tests are right-tailed tests, as I imagine. Your rejection region is always to the right of the critical value. These critical values determine the rejection region. And the p-values, we're not going to work with p-values. If you have software, all software programs will actually give you the p-value. In fact, it might not even give you the critical values. It would instead just give you the p-value, which is basically if you take this distribution, and if this is your test statistic, then the p-value is that area. Right? So we're not going to be doing the p-value process here. I will post the results of p-value calculations from software, but we will use the table and use the critical region method, or the rejection region. Okay, so the process for a goodness of fit test. First we have to determine the null and alternate hypothesis. By the way, this process is stepwise the same as chapters 8 and 9. In the null hypothesis, there's two options for a goodness of fit test. One, all the probabilities are the same. All right, and they look like 1 over k. So each category has an equal probability of occurring, sort of like with our dice there. Each outcome possibility, like a 1, 2, 3, 4, 5, 6, has the same probability, 1/6. You also might have a case where you have a specific expected probability, where these are specified, and we'll do an example like that in a minute. But you're saying, all right, the probability of outcome 1 is a given value, the probability of outcome 2 is a given value, on and on and on. As opposed to saying they're all equal, you actually give them a specific value. And then your alternate hypothesis basically says not the null, right? The probabilities are different from those specified in the null hypothesis. They're basically saying this is not true, right? And so if you end up rejecting the null hypothesis, basically you're saying there is not a good fit. And if you don't reject the null hypothesis, you're saying it's a pretty good fit to what I expected. Okay. So once you get the null and alternate, calculate the test statistic. First you want to calculate the expected frequencies, and that was back here where we took this formula right here, but whenever I covered it I did in the table. The expected frequencies is the probability times the total number of trials. So that formula is E sub I equals N times P sub I. So you need to calculate the expected frequencies and then calculate the test statistic using that formula. And it's easiest to do with the table. If you're doing it by hand, it's actually easiest to do with software. But if you're doing it by hand, building the table will also get you the test statistic. We're going to determine whether or not we reject or fail to reject the null hypothesis. Again, there are two equivalent methods, we can do the critical value method, where we find the critical value from table 5, which is not on that page. And if your test statistic is larger than the critical value, you reject H naught. The p-value method, you need software, but if the p-value is smaller than alpha, you're going to reject the null hypothesis. And alpha here is the significance level. All right. Make an understandable conclusion. And really, there's only a couple forms of this. If you reject, because the null hypothesis has a very specific, one of two very specific setups, we don't have the large array of options for our concluding statement. If you reject the null hypothesis, and you say there is sufficient evidence to conclude that the distribution of outcomes does not fit the expected distribution from the null hypothesis. And then specifically, and you go into whatever the specific is, whether we're talking about dice or distribution of rainy days or whatever that is. So you want to clarify things after this sentence. If you fail to reject the null hypothesis, there is not enough evidence to conclude that the distribution of outcomes does not fit the expected distribution from the null hypothesis. Specifically, and then you give some of the details of the problem at hand. The requirements, we need at least 5 for all of our expected frequencies. Right? And I'll show you that in a second. Oh, and if there's a sample, it should be a random sample. Okay, so here's our preliminary example. We roll a 6-sided die 60 times. The frequencies of the outcomes are given here in the first 2 columns. So we got 7 ones, 6 twos, 11 threes, 15 fours, 13 fives, 8 sixes. So look, and our expected frequencies are all 10. We'd expect 10 of each. So we got a lot more 4s than we expected, and a lot fewer 2s. So, you know, there's some reason to believe that the probabilities are not, that this maybe isn't a totally fair die. Okay, so what we're going to do, test the claim that this is a fair die. In other words, test the claim that the probabilities of all outcomes are all equal to 1/6. And we'll test at the 0.05 significance level. So some preliminary information, and we're looking at this test statistic and this. So we need to know these variables. N is the number of trials, so N is 60. All right. We got that. K is 6. That's the number of different outcomes. Degrees of freedom is K minus 1. So that's 5. And the significance level is 0.05. So the claim is that the die is fair. Right? Now, regardless of my claim, my null hypothesis is always that P1 equals P2 equals P3 are all the same, or that we have some prescribed, predetermined probabilities. But in this case, we're looking at probabilities that are all the same. So that's our null. And the alternate says the probabilities are not all equal to 1/6. It doesn't say what they are, it just says they're not all equal to 1/6. So we're going to calculate the expected frequencies. And so that's going to be in here. That's this column. Well, so if my probabilities from the null hypothesis are all 1/6, right, and there's 60 rolls, or 60 trials, then I'd expect 1/6 times 60, so that's E sub I times N. E sub I times N. Notice that comes from right here. Sorry, P sub I times N. These are the E sub I's. Okay, here we go. E sub I here is N times P sub I. Right, so when you take this times 60, which is what I did, that's just P sub I times N, we get the E sub I's. So you do this, and again, because all of the probabilities are equal, all of our expected frequencies are equal as well. Okay. Now we want to calculate the test statistic. So what this test statistic does, or says, is I take my observed outcomes, my number of observed outcomes from each possible outcome, subtract the expected, square that, divide by the expected, and add all those up. So it's a whole process, just like the formula for the standard deviation is a whole process. And if we do it in a table, it's really not that bad at all. So for each outcome, I have the observed, this is O sub I, O sub I, this is E sub I. So this column is O sub I minus E sub I squared divided by E sub I. So I keep doing that. I do it for each row. I get all of my individual terms in the sum, and then I add all these up. Add. And I get 6.40. So 6.400 is my test statistic. Right? So now, do we reject or fail to reject the null hypothesis? Well, if we take our degrees of freedom, 5, and we go to table 5, what you'll see is, let me erase this. We are 5 degrees of freedom. It's a 0.05 significance level. So my critical value is 11.070. 11.070. So what that means, if I'll draw the distribution up here. All right, woo. There. So it basically says, here's my critical value, 11.070. My rejection region is here. And if I take my test statistic, 6.4, that's over here. That's not in the rejection region. So we failed to reject the null hypothesis. If you use software, you get a p-value of 0.2692, which is larger than alpha, which is 0.05. So again, we failed to reject the null hypothesis by either method. And so let's take a look at what that means. We failed to reject. So the null hypothesis is up here. The null hypothesis is that all of the probabilities are the same. The null hypothesis is that the die is a fair die. And I have not rejected that. So that's good. That makes me think the die is probably fair, but I didn't really prove that it is fair. All I did was say there's not enough reason for me to believe that it's not fair. So the phrasing goes like this. There is not enough evidence to conclude that the distribution of outcomes does not fit the expected distribution from the null hypothesis. But that's rather cryptic, and somebody might not know what you're talking about when you're talking about a die. So specifically, there is not enough evidence to reject the claim that the die is fair. Right? We're not saying the die is fair. We're just saying there's no reason to believe. There's not a good enough reason to believe that it's not fair. Right? So good. Preliminary example completed. We'll get a your turn number 1. Right? Distribution of rainy days. You suspect that the number of rainy days in a certain city are not evenly distributed throughout the week. In a random sample of 100 rainy days, the frequencies are given in the second column of the table below. So we have our days and the frequency of rainy days. So we have Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. I order them with I index them with I. So that's what the 1, 2, 3, 4, 5, 6, 7 is all about. So there were 21 rainy days on Sunday, 9 on Mondays, 13 on Tuesdays, 23 on Wednesdays, 7 on Thursdays, 15, 12. All right. So the total number of rainy days, there's 100 rainy days, and this describes how they were distributed. All right. Okay. Test whether or not the number of all rainy days are evenly distributed throughout the week. Conduct this test at the 0.05 significance level. All right, so preliminary information. The number of trials is 100. That's found by adding up all the observed rainy days. The number of categories, the number of outcomes, is 7, 1 for each day, right? Degrees of freedom is k minus 1, which is 6. Significance level is 0.05. If we want to determine the null and alternate hypothesis, there is no specific claim. Notice the way this started off. This started off, test whether or not the number of all rainy days are evenly distributed, right? And so there is no specific claim, but the null hypothesis always takes on one specific form or the other. In this case, evenly distributed means that the probabilities of rain on each of the given days should be equal, right? They should all have the same probability of getting one of those rainy days. And the alternate is always easy. It's that the null hypothesis is not true. Not all the probabilities are equal to 1/7, right? Okay, so the assumed probabilities and expected frequencies are in the table. So let's start here. So the assumed probabilities from the null hypothesis is that the probabilities are all the same, right? For an even distribution, the probabilities will all be the same. And since there are 7 outcomes, it's 1/7 for each one. And so the expected number of rainy days in 100 trials, if the probabilities were all the same, would be n times p sub I. All right, so 14.3, 14.3. So if the number of rainy days was evenly distributed, you'd expect 14.3 of each. Of course, that's impossible. These are expected values, so it's okay if they can't be obtained. So those are the expected, and now we have to do observed, because look, we're looking at this formula. We're going to add up all the O sub i's minus E sub I squared divided by the E sub i's. All right. So we're going to look at this for each row. That's what this up here. O sub I minus E sub I all squared divided by E sub I. And so again, the 21 comes from here. The 14.3 comes from here. Don't forget to square it. Divide everything by E sub I. You get 3.139. If you do this for each row, you get all of these values. And then if you add these all up, you get 14.645. So the test statistic is 14.645. Boop, comes right from the bottom of that last column. So now we have to determine, do we reject or fail to reject the null hypothesis? Well, let's see, I have 6 degrees of freedom, 0.05 significance level. I go to my chi-square table. 6 degrees of freedom, 0.05 significance level, 12.592. That is my critical value. 12.592. And my test statistic is bigger. It's a right tail test. So I'm in the rejection region. Specifically, my rejection region, the critical value is 12.592. So the rejection region is over here. And my test statistic is certainly in that rejection region. So we reject the null hypothesis. If you have software, you can get a p-value of about 0.2032, which is smaller than alpha, which equals 0.05. So either way, you reject the null hypothesis. So what you do, let's go back here. We are rejecting this. So we certainly have good reason to believe that the days are not evenly distributed. The probabilities are not all equal to 1/7. So specifically, there is sufficient evidence to conclude that the distribution of outcomes does not fit the expected distribution from the null hypothesis. And while that is true, it is still somewhat cryptic. So to clarify that within the context of this specific example, we say specifically, the evidence suggests that the number of all rainy days are not evenly distributed throughout the week. Right? Little quick add-on question here. Does your conclusion change at the 0.01 significance level? Well, if you got the p-value, you can immediately say yes. Suddenly, the significance level is now smaller than the p-value, and I'll fail to reject the null hypothesis. But if you're a table user, you don't know about this p-value. But if you look at the critical value at the 0.01 significance level, we're no longer here. We are here, and the critical value is 16.812. And what that means, 16.812 is now the critical value, which means my rejection region now starts at 16.812. And my test statistic is no longer in the rejection region. Right? So I would fail to reject the null hypothesis. And I would basically say there's not enough evidence to suggest that the probabilities are not all equal to 1/7. Right? Or there's not enough evidence to conclude that the distribution is not even. All right. Your turn number 2, distribution of blood types, and this is an example where we have a null hypothesis that doesn't claim all of the probabilities to be the same. So we get into blood types here, and there are 4 groups as far as blood groups, and each one has an Rh positive and Rh negative version. So that gives us 8 different blood types: O positive, O negative, A positive, A negative, and so on. And according to the American Association of Blood Banks, the distribution of these types across the country are given here. 38% of us have O positive, 7% O negative, 34% A positive, and so on. In a sample of 800 donors at some regional blood bank, the frequency table below gives the distribution, right? From the 800 donors at that regional bank. So we have different types, and so this is what I mean. So I had 800 donors, and here's the distribution of their blood types. 310 were O positive, 71 were O negative, 235 were A positive, and so on. And we want to know, test the claim that the distribution of blood types from this region of donors does not fit the national distribution. In other words, is this regional distribution different from the national distribution based on our sample of 800 donors? Test this claim at the 0.01 significance level. Okay, so our preliminary information, n equals 800, that comes from the total of the observed frequencies. K is 8, that's the number of different possible outcomes. Degrees of freedom is K minus 1. Significance level is 0.01. So basically, the claim here is that the distribution of blood types does not fit the national distribution. But the null hypothesis always has one of 2 forms. It's that the probabilities are all equal, or that the probabilities are given some prescribed values. And that's what this is saying here. The prescribed values come from the national distribution. Right? According to the national distribution, O positive should take up 38%, or there should be a 0.38 probability that a person has type O positive. O negative should have 0.07, and that came from here. 38%, 0.38. 7%, 0.07. Right? So these assumed probabilities in the null hypothesis come from the national distribution, because that's what we're comparing. We're asking, does the regional distribution fit the national distribution? So our null hypothesis is that P1 equals 0.38, that's the 31%. P2 is 0.07, on and on and on until P8 is 0.01, and that's represented by the AB negative. Okay. The alternate hypothesis is that the probabilities are not equal to their respective values up here. We're saying the alternate hypothesis is basically that the null hypothesis is not true. Okay, so we're going to calculate the test statistic by we're going to take the sum of all of these, right? From I equals 1 to K. All right, so we have to calculate our expected frequencies, but that's just 800 times P sub I. So it's N times P sub I gives you 304. And that's P sub 1 in this case. N times P sub 1, so it's 800 times 0.38 gives you 304. 800 times 0.07 gives you 56. 800 times 0.34 gives you 272. So if there were 800 donors, and if it matched the national probabilities or the national distribution, this is actually how many you would expect in each category. And these are what you got. So we're going to subtract the observed minus the expected, square it, and divide by the expected. And so when you do that, you get this 310 comes from over here, from the observed. 304 comes from the expected. Don't forget to square it and divide by the expected. So you get 0.118 here. For O negative, 4.018. For A positive, 5.03. So you keep doing this and then you add them. And you get a test statistic of 23.74. Right? The test statistic, test stat, chi-squared equals 23.724. So we now have to determine whether reject or fail to reject the null hypothesis. We go to table 5. With 7 degrees of freedom, 0.01 significance level. 7 degrees of freedom. 0.01 significance level, 18.475 is our critical value. 18.475. And our test statistic, 23.724, is in the rejection region. It's bigger than 18.475. In other words, if I do a quick drawing here, the critical value is 18.475. The rejection region is everything to the right of there. When I look at my test statistic, it is indeed in the rejection region. So I reject the null hypothesis. If you have software, you get a p-value of 0.0127, and that is smaller than alpha, which is 0.01. Sorry, the p-value is 0.00. I said 10 last time. 0.00127, which is indeed smaller than alpha. So again, you reject the null hypothesis. So what that means is we reject the null hypothesis, right? We reject this. So we're saying that the probabilities are not equal to the national distribution. So with regards to the hypothesis test, there is sufficient evidence to conclude that the distribution of outcomes does not fit the expected distribution from the null hypothesis. Again, that is fairly cryptic, and somebody might not know what you're talking about with all the hypothesis in there. So specifically, the data supports the claim that the distribution of blood types from this region of donors does not fit the national distribution. And that's a sentence that makes sense, and almost anybody could understand it, even if they have never taken a statistics course. All right, so that wraps up chapter 11.1. I will see you come chapter 11.2. Take care. Bye.